This is the final video of the Collider series. Its goal is to combine all the things you learn in the circles and spheres video, lines and planes video, and put it into something a little more useful and more complex objects. So if you haven't watched those videos, make sure to watch those because it's not going to make a lot of sense until you've seen those.
Ow! I'm studying! I promise!
So in previous videos, we looked at lines and circles, and we talked a little bit about how to combine the circles with lines in order to get something a little more usable as a line. So this one's going to look a little more deeper into that concept of combining different types of colliders into one object. Normal objects, you're going to have something kind of like that, where I've shown you in the previous video, where you have a large sphere around a complex object to see if something's close enough to check. But we never actually talked about how to make them actually collide and do the collisions between those complex objects. So that's what this video covers. So if you take a look at this one, it has two different places that the complex objects are actually colliding. And we're going to look a little deeper into those particular objects to see what's really going on and how to isolate those particular collisions to make one bounce instead of a whole lot of ones with different lines and circles colliding, which is going to be really weird if you don't handle it properly. If we take a look at this complex object, it looks like just a series of lines. But if you look a little closer, you'll see there's little circles at each of the little corner points between those lines. But just like we had in the line video, we put circles at each end of the line, we kind of did the same thing here. But instead of it being on each end of the line, which would end up doubling up points, we'd have points for every corner inside the object, and we connect those points with individual lines that are one-sided facing the outside of the object. That's kind of up to you to figure out which way is the outside. Complex objects get kind of confusing, so it's just a design feature. We'll get into why it's a one-sided line a little bit later. If you look a little closer when these things collide, like in this particular image from before, you see that there's two different places that look like they're just touching. But if we zoom in a little closer, like this one here, one of those collisions actually has the corner point bypassing into the other object, and the individual lines are intersecting. So that's that troubled situation from that last video that we kind of have to accommodate for because it's going to happen. And with that particular collision, if you look at the other side, which was just touching like that one, you'll see that the circles and the lines are actually colliding with the line, and it becomes a little more problem again. So with that, we have a bit of an issue. How do we manage those particular collisions? We also have multiple of them all at one time, all coming into one collision. So we have to average them out and make something actually useful. So one of the other problems we have with a complex object like this is all the number of objects that are built into the complex objects. You have tons of lines, tons of circles, and you may not want to have an object with 100 items in it trying to combine and with another 100 objects to see which parts are colliding, if any at all. If you do the math, you can easily end up in the thousands of combinations that you have to check for, and that's kind of a waste for time. So what we can do is something like this, where you have the individual circles inside of the detection range, and you link those circles with the actual objects in that region to determine these are the ones that have the potential of having objects, and we can eliminate all the other ones from having to be checked. But instead of having thousands and thousands of collisions that we have to check for, we can kind of limit it down to maybe a dozen or less than 100, which is a lot faster in the long run when you're dealing with dozens of objects floating around close to each other. So before we actually get into the code of how to make this particular class, there's something that has to be covered. So an abstract class is kind of a partial piece of a class that can be used as something that inherited by other classes. So if you've heard of inheritance, this is kind of a modified version of that called polymorphism. So the idea is you make an abstract class that can actually exist, and you link other items to it as subtypes of it. And then the actual subtypes handle the functions which are declared inside of the actual abstract class. If you ever worked with C++, for example, you define the particular functions you want in one portion of the class, and then you define the functions in another portion of the class. It's the same kind of idea, where you define the actual functions and some of the basic types that you want to have stored in the abstract, and then the actual subtypes end up having all the actual definitions for how it's run. Problem with this is that you can have dozens of subtypes. You don't know which one you're actually going to be working with, which is an advantage and a disadvantage because you don't know which particular version of that function is going to run when you're trying to debug something. So it's a little more difficult to figure it out, and you kind of have to dig farther to determine things. I'll kind of describe this in the code of how to circumvent some of those debugging problems. So as I mentioned before, we're going to have an abstract class that we're going to have for all the different colliders we have, so a circle or a line. And so we can do the debugging a little easier, we're going to have an enum that defines if it's a circle or a line, which we store when we create the actual object. So when we're debugging, we can go back and reference which one we're working with, so we know which version of the functions we have to look at. Inside of this, we also have a reference back to the original outside object for the main collider, a center point for this particular radius that we're going to work with, whether it be a line or a circle. But it's going to be in reference to the actual center point of the main object. So not the world position, but actually where it is in reference to the actual center of the main object we're working with. It makes it easier to do rotation physics and things like that later on. And we're going to have some kind of radius around that particular center point, so we know if something's close enough to bother checking. We have two abstract functions. We have is colliding and handle collision. So this is going to determine if it's close enough to bother having a collision in the first place. And this one will actually handle the collision physics itself and output the force and the amount of overlap to correct. These are not defined in here, they're just declared. We actually define what those things mean inside of the types, subtypes that we're actually working with. So either a circle or a line. You can make more later on depending on what you want to work with. Inside of them, like in a circle's case, we have an optional link to all the lines that use that particular point as a vertex inside the outside of the box. So you don't have to use it, it's just kind of a handy reference back and forth. Depends on how you want to make your game. And then we're going to actually define what these particular functions mean. If they're not there, it won't compile. So we have to have a definition for what these mean. I'm not going to go over actually what the definitions and coding of these are, because that was covered in the first two videos. For the line, we're going to have the start point and end point. You could make references back to the circles if you wanted, instead of having the actual point just stored. That's up to you. And then you have the normal line stuff, tangent, segment, length, and all the other options you might put along in there as well, along with any kind of links that you would have that go back to the endpoints over here. It's up to you if you want to do this, and the normal function declarations here. If you remember back to the early image where I had a bunch of circles inside the main detection area that I called zones. So these particular detection zones are going to be placed throughout the actual object to determine what is actually associated to that area, so we can focus in where we're actually going to do all of our calculations. That's going to have a center point relative back to the actual center of the actual main object. It's going to have a radius, just like every circle, and a link back to the main collider. Then there's a bunch of lists here. Kind of optional how you want to do this. You can separate it out by different types, or you can have one main list that contains everything, because after all, we have this particular enum back here, which is stored to determine what the actual type is. And then there's a simple is colliding function, which takes a center point and a radius and determines if the actual circles are overlapping. Very simple. This is done in the first video. Normally I wouldn't put all of the classes into one file, but it makes it easier for this particular video. So to begin with, we're going to have some kind of constants at the top. So in this case, some default ranges that we have. So we're going to have like an extra buffer for the overall radius from the center point to the farthest corner, plus a little bit buffer in order to determine what this detect radius is going to be. And this kind of all these little corners, how much radius are they going to have? Whatever it works for your world, you can set there. Then you have a center point for the actual object itself. You have the physics stuff like momentum and mass. You can add other things along with this, like rotation, torque, and so on and so forth. But I simplified it for this video. I have a center point for the mass because it might be different than the actual center point. This is going to be really important for rotation physics. For this video, it's not going to come in play, but note that it's going to be relative to the center position, not its own world position. Then you're going to have some lists. They're going to have the lines, circles, or you can combine them into one large list. It doesn't really matter. It's up to you. Notice that it has the base simple collider type and not the actual base and circle types. The reason why I do that is because I really don't care most of the time if I'm working with lines or circles, because the function call is the same. I just want to know if they're actually colliding and then tell them to deal with their own physics and give me back the force and overlap correction. So I don't care if it's a line or a circle most of the time. And if I really want to know, I have the enum to go back and check that. Or I can just separate them into two lists if I really care for my yang. Then there's actually the zones, this radius that are inside of the main detector range that I showed you early on. And those are kept in a separate list, easy to work with. They have their own references to these, so I don't have to worry about these all that often. I have some optional dictionaries that will come up a little bit later. But then I have major function calls. So all the things I need to add in to build the object. So edges, detect zones, and so on. I'm not going to go over that. That's pretty simple stuff. The main focus is going to be, is it colliding? When it's colliding, I need to get those particular calculations done. And once I have those calculations, I need to push the force values and overlap into here so I can actually work with it for my physics each frame. So before we actually look at the code in order to handle the detection of collisions, let's go ahead and take a look again at this particular image we had at the beginning. We have two different areas that are actually colliding or have potential for collisions, and we can actually separate those out from the whole object by looking at the zones that we put up originally and isolate those particular zones. Zoom in on those particular areas and look at the first collision like this one. We see that there are two lines intersecting with two lines, and the circles have passed through the actual lines. So we have two intersections of lines to deal with. If we look at the other collision area, we see that we have two lines intersecting with one line, and the circles pass through yet again. We have some weird situations where we can have one object colliding with multiple others. So it's not just a line versus a circle or a line versus a line. We can have any combination of those things with one colliding with multiple other ones at the same time. So we kind of have to account for that in the code. Also, if you have this particular weird potential one, it's not in this particular example, but we have a concave object and we have different collisions that are going to have some really weird potential if we don't handle the things properly. So we have multiple objects colliding with one line, we have another pass through on another area, and depending on how you work with the collision and how you work with the overlap, put it all together again, you might end up with the object passing through the other object just because the collisions were handled improperly. So we're kind of actually work with that later on. But detecting these particular issues becomes difficult if we don't handle it properly. So for the find collision function, I'm going to take an external collider, so an exact copy of what I already have here, but for a different item, and compare it to the actual internal collider set. I'm going to output all the found collisions between the two items. And I'm going to return true if anything was found at all. And it's false if there's something kind of wrong or if there was no collisions found. So maybe if I forgot and left this as a null, it would still return false. I'm going to make a couple lists. So in here I have a dictionary that's also repeated up in the main class. This here. So it's either up to you if you want to have one internal to the function or one for the class. This might be a little more fast because you don't have to keep recreating dictionaries and lists, but at the same time you might have multiple calls going into this collider, so these might be overriding each other for threads and things like that, so it may become a problem. So this might be your better option. Just kind of take the performance hit. If you use the one that's in the class, you're going to have to keep clearing it out over and over again. Just be careful when you do that because you have circular references back here. So a circle is going to reference a line is going to reference a circle, and they're also going to be stored here. So things might get a little weird. You might end up removing things from memory that you didn't mean to, or things might get stuck in memory because the circular references are keeping things there. This is very language dependent. I've had issues with C#, but in something like C++, you probably wouldn't have this problem. Once you get everything ready to go, then you go in and actually see if there's any collisions possible between zones of the different objects. So if it is, I'm going to take an external collider, look at all of the zones there, look at the zones internally. If there are, I'm going to mark down what those external zones are. And for every external zone that I find is colliding with itself, I'm then going to take a look at those zones and determine what the actual items inside of those zones are actually colliding. So which lines, which circles are colliding with circles and lines from the external zone to the internal. This little block here, you can take this particular output and just output it right out of the main function line. But I do this separately because I might want to store it for other purposes, such as later use for sound, particle generation, whatever I want. So you might have to keep it separate. You might be able to output it directly. It's up to you. The main thing is that if you copy it here and then want to output it directly, you still have to make sure that you're copying things properly. So I move all the information from this dictionary to a new dictionary. I have to add a range, but make sure you do the add to by array here, not just the list itself or just a copy of the directory or dictionary itself. The reason why is that if I go through here and hit clear on this particular list, even though it's stored in this external list somewhere else in memory, it's going to clear both lists. Or if I clear it here, it's going to come in and start clearing all the collisions inside of this particular class because it's the same exact thing. If I copy to an array, it's no longer exactly the same object. The clears are now independent. It's no longer an issue. And then the whole thing returns true if I've found any collisions whatsoever and have stored them. So as I mentioned before, this particular function here, it compares the individual zones, is collide possible. So it just goes through and does a quick comparison of circles. Are they close enough together to justify the actual overlap of circles? If they are, then I go ahead and just store it and get ready to output it, which is done by passing a true out if there is any particular zones possible for collisions. This doesn't mean that anything inside of it is actually colliding. It just means the circles are overlapping. Note that I'm using the is colliding for the particular zone, not the is colliding that was done inside of this function or inside of the line or the circles up here. Just using the base class for the zone itself. So the last function that goes through is this one here, the external zone here. What this is going to do is find and output all of the individual lines and circles that are actually overlapping with each other. And it will actually define which collider is overlapping with which particular items. Maybe make a list of all the different possible collisions. I'm going to find zones that I've input here. I'm then going to look through all of those zones, collider zones here. It's colliding. Then I know that I need to add all the circles and all the lines that are possible to be inside of the zones and add them to my list. Once all of the items are added to my list, then I can go through each individual item and determine if they're colliding. So I have an external collider for each one of the external colliders. Check the internal collider. For all of these particular internal colliders here, then I go through and determine, is it colliding? Notice that I don't care if it's a line or a circle. I don't care if one is a circle, one's a line, or vice versa. It doesn't matter. I've simplified it by using that abstract class and polymorphism. If it's colliding, then I can just go ahead and add that collider to the dictionary, add a list for all the ones that are going to be associated to it, and now I add the internal colliders to this list. I could have done this internal and have a list of externals. It doesn't really matter. Just make sure you note it and keep track of that because it can start to matter later on. So just be consistent throughout your programming. So now that I know what all the objects are that are colliding, I go out and I return true if there are any existing at all. And then, because this is out, being passed outward, ends up going back out to this particular function that it started with in the first place. I add them to a range and now output, yes, there were collisions. Here are the particular list of items that are colliding. And that would go back to the physics engine for later use. So now that we know where all the actual collisions are actually occurring, we can actually just take those individual interactions and start actually doing something with them, determine if we're supposed to do something with them. What we can do is we take the actual items like we have in the first collision, and we apply the momentum lines from the main object and their mass to those particular items. We don't separate out this particular portion of mass is here or particular momentum is on this. It's just all the same for all their objects. It's just going to simplify everything. So once we have that, we can actually just take those particular momentums, determine is the momentum passing through the right direction of the line, and if it is, then we can go ahead and start calculating the force. The code is actually very simple. We just refer back to what we saw in the previous videos and determine what's the force that we're supposed to apply. Handling collisions themselves is actually incredibly simple. We've already defined all the known interactions inside of the collision portion up here. So all we have to do is take our external collider and an internal collider, and then look at all of the known interactions and run through them very quickly with a simple loop. So for every E that we have in the known interaction, so internal collider or the external collider, depending on how you set up your dictionary, and then for every one of the items inside the list associated to that key, we're going to take that key, we're going to call the handle collision function, which is right here, which if it's a circle or a line is called here or here. I really don't care inside of this function. It just doesn't matter to me. So why do I don't really care if it's a line or a circle. So very simple, easy to read. Just handle the collision, do whatever you have to do, and output what force and overlap I need to deal with on my side. Every time I have a new one, I count it up. I'll explain this in a minute. And I take the overall forces and I sum them together. I'm going to pause this looking at this particular function for a little bit more information of how we're going to work with this particular piece here in order to prevent an excessive amount of force being applied to this object. So now that we have all of the forces that are in each individual collision, it would make sense just to sum them together and get one large combined force. Problem is that that would be probably 15, 20 times larger than what we're supposed to have because we're working with the mass of the actual object, not some little small portion of mass in that particular area of the object. Or the speed is also being combined in 15, 20 different locations. Now it's way too high. So what we can do is we take it and have this complex particular one, and we just start averaging them together. So instead of having a bunch of little forces going all over the place, we take all the original forces we have, now sum them together, divide it by the number of forces. It gets us pretty close. Likewise, if we have overlap correction, we just move them around based off of the actual values that we've received at each one of those locations. You get something like this, where it's moved way too far in one direction and it started to actually push itself through another area, which is also why we deal with only having one-sided lines and things. So if things are going to go through another area of the object in these convex shapes. It's just the way it works. So what we can do is we take all the overlap corrections we had, and then we sum them together and divide by the quantity. Now we have something that's kind of close. It may not completely eject it from the actual object, but over a few frames, it's going to self-correct and it won't be a problem anymore. Returning back to our handle collisions function, we have a summed up total of forces and overlap correction and a count of all of the collisions that we've found. So if any exist, we're going to divide the force and overlap by the number of collisions that we found to give us our overall average force and overlap correction that we need to do. It's going to be close enough for our game purposes. The user's probably never going to notice maybe some really unusual occurrences. They might question whether it was realistic or not, but it's close enough. And then we're going to take it and apply it to the main object, and then apply the opposite direction force and opposite direction overlap correction to the external. That way they move apart from each other properly. The big key is that in your physics engine, make sure that you're only calling handle collision for one of these two objects. So you're going to have some kind of prevention method to make sure that this is only being done once, which you want to do anyways because you really don't want to repeat these calculations over and over again. They're rather extensive. There's no reason to double your work. And then you return true if there were any collisions found. There are a couple extra functions that are down here, apply force and apply overlap. It's not really important for this video, it's just a matter of summing all the forces between all the different collisions. And then at the very end of the frame, you end up working with these, combine them together, maybe you take an average, and then you modify the overall center position and momentum of the object here at the end of the frame. The main known issue for this particular method of doing collisions is that we know things are going to overlap along the way. So if we just assume that it's going to happen a lot, and we start making things one-sided, we can kind of correct for it by just simplifying the math and making it simpler in the long run. It's a known problem, it's going to happen, but it also allows us to have concave shapes instead of just convex ones, so things might get trapped a little bit, but they'll kind of work themselves out. Also, if we do that overlap correction with the divider like I had talked about in previous videos, if you have a large stack of items, they'll kind of work themselves apart over time. And if they don't do it quickly, it just kind of looks like they're crushing together depending on the object. It might actually be okay. It might be a pleasant effect that you're looking for. You kind of have to play with the variables a little bit in order to determine what's the right version, what's the right value that you want. And eventually kind of come up with something that gives you a close enough representation for what you're looking for. And then the outliers don't happen enough to actually matter that much. So this is the last video out of the non-rotating colliders series. Hopefully it was useful for you. If you plan on using these, let me know. I would love to hear your ideas. I've used these basic colliders for a particular game already. And even with the non-rotating, you can get some nice effects based off of just combining them together in something useful.
Ow! I'm studying! I promise!
That bounced a little more than I thought it would.